No. This gives us the 6 GM over R, but the problem asks for it in terms of escape velocity. So then you have to then work back and say oh, well, what was escape velocity? It's 2 GM, and so we have 6 GM, and you can see it's root 3. Okay? That was a conversation earlier today. Who put these desks? They're not helping. I'm short. I can't reach over them. You know what I need? That was a great question. So they have some wellness coaches coming in to help us, which we need a ton. You may have noticed that your teachers are hanging on by a very thin thread. Myself included to some extent. So that's going to be nice to maybe talk to somebody about the fact that this is challenging. And then I could always do some work. I still haven't made the videos for the chapter 13 homework I assigned you, which makes me very upset with myself. But what are you going to do? Again, see part 1 of the conversation, hanging on by thin thread. And then, I have to take Dexter, my 8-year-old, to the orthodontist.
Braces?
So they do a really smart thing now, so that even when he's 8, right, he doesn't even have all his baby teeth aren't even out. I'm like, we really need braces now? Well, they do a really smart thing where they put a spreader in, and they spread the teeth out. Now, at 8. And so what happens is, all the teeth can now come in. So some of his adult teeth are overlapping some other ones. I think to spread it out so they can all move into line. If you wait, the old way was we'll just wait till you get all your adult teeth and then we'll just straighten them all out. And that is just not as effective. It's just more painful, more money, more time. Let's just spread the teeth out now. It actually comes from a fascinating phenomenon where the United States is a mix of a lot of different ethnicities. And so we have some problems because if you get 2 different ethnic groups, let's say someone from Western Europe, and they have babies with someone from, let's say, Southeast Asia. Those 2 ethnic groups have different size things. The teeth are different. People from Southeast Asia have very small features and very small teeth, but someone from Northwest Europe will have very large features and very large teeth, and then you get a problem because what if a kid with large teeth has a very small mouth that they're supposed to go into? We get these problems in America because it's ostensibly a melting pot, but not exactly. That's why we have braces. That's why other countries don't do braces as much, like Norway. They don't do braces in Norway because it's one ethnic group throughout the entire country, right?
Fascinating.
Isn't it? It's also why when people say we should adopt Norway's educational system. No, we definitely should not. Okay? They have one religion, one culture, one ethnicity that literally they haven't changed anything for 100 years. And when you get to high school level, if they don't think that you're going to be successful in high school, they put you into a trade school. So you look at their high school test score numbers. Well, if I lop off the bottom third here, it just doesn't even make any sense. I mean, it's not that you're not testing the same things, and it's very, very annoying. They haven't changed the curriculum in Norway for 30 years. So all the teachers that are teaching now are teaching the exact same curriculum that they experienced when they were students. But they don't have any reason to change. Why would they change? It's the same culture, it's the same curriculum, they're good, right? And they always put out these things in terms of percentages, which is so dumb because Norway is this really small country, right? And so if you look at the number of qualified technical, in a technical sense, qualified high school students that we put out every year, even though the percentage is lower than, let's say, Norway, the actual number is like 10 times as many. Because we have that many more students that are successful than a school like that. So don't listen to the rhetoric. Yeah.
Is that per capita or just as like based on population?
I think it's per capita. I don't know. I used to read this stuff before I had kids, but I don't anymore because I like that much. All right. Oh, we're doing a thing. We're actually doing something today. We got to finish the last 5, right? Is that right? Don't be so funny. Oh, this one is actually hard though. Okay. All right, so here's what's cool, is that what we have with the Earth-Moon system, for example, if we look at our Earth-Moon system, is we have this idea that the moon goes around the Earth, and it does, right? It does, and our evidence of that is the phases of the moon. So I know that not only does the moon go around the Earth, but I know how much time it takes because I just look at it every night. I'm feeling really good about that. What we find out to be true, though, is this is not exactly true. What's happening is because these are Newton's third law force pairs, they're actually orbiting, and it's not even that they're orbiting each other. What they are orbiting is each of them is orbiting the center of mass. It just turns out that because the Earth is more massive, so much more massive than the moon, the center of mass of the Earth-Moon system is within the Earth. And so if you were to watch the center of the Earth go around, the center of the Earth actually goes around the center of mass. But the Earth it's inside the Earth, so it actually only just like wobbles around a little bit. Where the moon doesn't really go around the Earth's center, it actually goes around the center of mass of the Earth-Moon system. Come on, that's pretty cool. So what would happen if the moon were more close to the mass of the Earth? If the moon were more close to the mass of the Earth, the center of mass would move out here, and then you'd have two things happening. The Earth would rotate around the center of mass, and the moon would also rotate around the center of mass. And now what it looks like is they're kind of going like this, right? They're kind of going like this, not really revolving around each other, but revolving around the center of mass between them. This happens not at the planetary level, although to be honest, this would happen. So Pluto is one of our dwarf planets, and when they looked at it, when they first saw it, it's a tiny little, just like blurry little speck. But it had, like, they knew it wasn't a star because it was too close and not really bright enough. And once they were able to resolve it a little bit better with more powerful telescopes, they realized they were actually looking at two things: Pluto and then a moon of Pluto called Charon, which is, dude, what is up?
Hi.
Hi.
Can I just listen in for a sec?
Have a seat. Or stand or whatever. So these two things, they are very close in mass and they revolve around each other. Is that cool? All right, so what are we doing? This manifests in binary star systems. So when you look up into the night sky, 2/3 of the things that you see are actually binary stars. They look like one because we're so far away, but they're actually two stars relatively close to one another, revolving around the combined center of mass. So in this particular problem, what do we got? We got two stars of equal mass. And then, oh, that was nice. All right, here we go. And what is this? How far is that?
D.
Oh, so the whole thing is D. All right, D. And so this would be every radius. Okay. Is that cool? We got a conceptual setup here? What's the question? Which of the following is a correct, I don't know, how are we supposed to know? All right, well, let's start with our conceptual setup. What do we know? So if I look at either one of these, this is the gravitational force and this is the centrifugal force, right? Okay. What do I know about those two things? Is that cool? Okay. Now, this is where the wheels fall off the cart. So try to focus on this. You ready? In this problem, if we go back and compare it to the Earth Moon, we were using the distance in the gravitational force formula as the radius. But when I look at this one over here, this is one of the stars, this is the other star. But this distance is the radius, and this is the distance between them. So I think the real problem with this is that because of the way it's a two-star system here, the R here and the D here aren't the same. So they can't just magically disappear in the equation. Right? But there's probably a relationship here between these two things, yeah? All right? Check your neighbor. What's the relationship between the R and the D in this one? Check your neighbor real quick, see what your neighbor says. What do you think?
Yeah, R is half.
Yeah.
Is it that simple?
Yes.
All right. Well, if it's easy, it's easy. So what is the, so they're in terms of D, right? So D is equal to 2R, okay? Or what would that mean? R is equal to half D, is that right? All right, I'm good here. So one of the M's magically disappears, so I end up with V squared over 1/2 D is equal to G over D squared. So what does that leave us with? Is that right? Is that right? Is that an answer? I can't wait to see if that's the answer. GM over 2D, that's B. Oh my gosh, it's like the moment of truth, I can't wait. It is the right answer. That was awesome. So, this actually, that same problem manifests on your homework 2 from chapter 13. Is that cool? So, if you have things orbiting around each other and not one orbiting around another one, keep in mind that the R and the D are going to be different. Cool? All right. A newly discovered planet is found to have twice the radius and 5 times the mass of Earth. The acceleration due to gravity on the surface is G. The acceleration due to gravity of the new planet is... Okay. So, this is a problem we've seen. Yes? So, let's just crank it out. G for Earth is equal to G, mass of the Earth, over radius of the Earth squared. G for my new planet is equal to G times, what's the new mass?
5.
5.
5 times Earth.
And what about the radius?
2 times 3.
And again, don't forget, you're changing the R, but it is in parentheses, true? So G for the new planet is going to be equal to, well, I got 5 on top and 4 on the bottom. 5 fourths, G M E over R squared. Is that cool? And this, you'll notice this, is the mass, is the G value for the Earth. Yes or no? 5 fourths, yeah? Cool? I love this one. All right. So this one. even a blind squirrel finds a nut occasionally. Okay. So what is it? 4? This is 49m, and that's little m. This one's little m. Does it give us our velocity? What's it say? 5? V0, and then what's this one then? V0? Is that what it says? Okay. And that's RA. Oh, so there's anything. Fantastic. A moon of mass little m orbits a planet of mass 49m in an elliptical orbit as shown. When the moon is at point A, the distance from the center is RA and the speed is V0. When the moon is at point B, the speed is 5V0. When the moon is at point A, the distance from the center of the planet-moon system is most nearly. Okay. Well, so when I think about this, is basically we're trying to solve for RB, correct? Well, remember from yesterday that at these 2 points, what do you know about the angular momentum? It's conserved, right? So the angular momentum at A is equal to the angular momentum at B. Another way you can consider this is angular momentum for a point particle is going to be mr squared times v over r. So it's equal to mrv. Which one we had yesterday? So this is the A side, this is the B side. The m's magically disappear, so I end up with RA at VA is equal to RB at VB. And this is the same result we had yesterday. So if this is 5 times faster, what does that mean about RB? The distance is 1/5. I want you to get a hold of me in the middle of the school day. So that's 5 times. So that's not the question. So first of all, I think this is a typo here, or it's a typo here. What is the problem? When the moon is at point A, the distance for the moon to the... So that's definitely a typo. I don't know what that means here.
Well, I think it's like in terms of RA, right? I don't know, I definitely got it wrong.
I just want to maybe find the center of mass when it's of the moon and the planet.
Oh, is that what it's asking?
Yeah, when the moon is at A.
Oh, that's really interesting. Okay, so I didn't realize what it was asking, and I'm glad Stephen pointed out. This is really interesting, because I asked, well, if I'm looking from the center here, I know what this is, but that's not actually what it's asking. It's asking from the center of mass. So we gotta take a whole step back and be like, well, how are we gonna find the center of mass between these 2 things? Remember that if I want to find the position of the center of mass, I'm going to go m1 x1 plus m2 x2 all divided by m1 plus m2. So mass of 1 is, you have more than enough information to complete quiz A. Please complete quiz A before tomorrow. Okay? Please complete quiz A before tomorrow.